Thank you for the invitation. So I intend to speak in a very elementary way. As I was told, it's a general colloquium, and so I apologize by advance if this is too much elementary. Okay? So I will just present first a kind of sketch of the talk. So weak dependence is something related first to independence. So I will recall some very simple feature from independence and how to weaken the notion of independence. Then I will speak about some alternative extensions, alternative to independence. And then I will rapidly introduce some one weak dependence notion by using the previous ideas. And here, okay, there will be some examples, some models of interest. So very simple models. And then I will try to speak of some models of time series. And explain how to get some limit theorem. That means I will explain about moment inequalities, and also about Lindeberg method. So this is what I want to say. So the first thing is there are very simple things. As I was saying, the first thing is concerned by independence, and so as usual, when you have two events, P of A and B is P of A times P of B is the standard definition of independence for two events. Now, if A is in some sigma algebra, that I will write P because it will be the past algebra of the past, and B is in some sigma algebra of the future, then it can be written also that the covariance between any functions of P and any functions of F. Yes, I am sorry. P is generated by some random variables. That means, and the F will be generated by some random variable, which will be the future. To settle the things, the idea is very simple. You have the past here, which is denominated a way to speak of some points. Some points where you observe a process, and the future is this way, so some points also, and so P is just a vector x e1 until x eu, and F is the vector x g1 until x gv. Okay, so that's the independence of those random variables F and P may be written only like that. This is 0 for all functions, or at least for enough functions which are measurable and bounded. Okay, so there are clearly two ways to define, to extend the notions of independence. One is based on sigma algebras. I mean, there was a notion which was introduced by Rosenblatt, and to define independence between approximate independence of two sigma algebra, the simplest thing was to say, okay, that's the supremum of P of A and B minus P of A times P of B for A and B in the past and in the future respectively. So this is called, there is a notion from ergodic theory which is closely related to this, but which essentially doesn't involve such a supremum. That's why this is called strong mixing. That's uniform notions. And here, what the expression of this thing, I'm sorry, is what we will call alpha of R, where R is just the time left between the past and the future. Okay, so this is a very natural way to define asymptotic independence between those sigma algebras here. But is that enough? That's not clear. I will come on a very simple example to explain that it is not always sufficient. So one example is a very simple one, that it is given by this equation where ct are Bernoulli distributed, that means 0 and 1 with probability 1/2. Okay? And so there is a stationary solution for this equation which writes sum from k equals 0 to infinity of 2 minus 1 minus k, certainly ct minus k. Okay, that's, it looks a bit complicated to understand, but you see when you plug xt minus 1 into this expression, you will get ct divided 2 plus ct minus 1 divided 4, and so on and so on. This means that in the basis 2, this may be also written 0 ct minus 1, ct minus 2, and so on. Okay? And the thing is that there is something between the sigma algebras generated by xt and xt minus 1, which is clear, is that xt is just a function. There is a function, how to call this, of xt, which is xt minus 1. This is a function which consists in just suppressing this digit, and that's it. That means xt minus 1 is in fact the fractional part of 2 times xt. Okay, so the sigma algebras are included into each other's, and in this case, when you want to work with this story, it will not apparently work. So for this, you need to consider, for instance, x0, the set x0 is less than 1/2. So this set may be also written as something like xr is in a set ER, which is the union of 2 at the power. So ER is just a union of intervals gr from g equals 1 to 2 at the power r, where the length of I don't know how to, no, not let's say the Lebesgue measure of those intervals is the same. It's just 2 at the power minus 1 minus r. So when you use this, you just see that P of A inter A. So here this is just minus P of A. P of A is just less than alpha of r, but it is also exactly equal to 1 over 2 minus 1 over 2 times 1 over 2. That means alpha of r is more than 1/4. So this is a very simple example which shows that even the simplest models to be used are not necessarily mixing, in the sense of Rosenblatt, and there were lots of literature on the subject. For beginners, I should suggest a treatise in 3 volumes, which was written by Bradley in 2007. Okay, so the theory is completely clean, but the problem is about those things. Another thing is that as I want to pretend myself as a statistician, I want to use the main tool of statisticians, which is the covariance. So covariances are not enough to determine a stochastic independence, but at least what you know is that if P and F are independent random variables, and if the suitable moment exists, then you know that the covariance between P and F is 0. I suppose just that this expression exists. Now there are some examples where the converse also exists, which is quite interesting, I think. The first example, maybe I will say it, is if P and F take values into a very simple set, which has just 2 points, then in this case the converse exists. How to prove this? Just I will explicit the covariance between 2 such random variables. That just the probability that P is F is 1 minus the probability that P is F. P is 1 times the probability that F is 1. So if you remember what is independence as stated before, this means that you don't have all those things. So this expression should be is 0, but in order to prove independence, you should prove that this expression, probability that P is A, F is B, should be equal to the probability that P is A times the probability that F is B. And so this should be done for all the possible values A, B. That's not a lot, because A and B are in the set 0, 1. That means here the simple definition of orthogonality, of the fact that covariance is 0, implies that 1/4 of the work is already done. You see, I just have here the case A, B is 1, 1. Now, by using very simple manipulation on the covariance, it can be noticed that the covariance between 1 minus P and F is also 0, and this fills the case AB is 0, 1. Now, and analog things like 1 minus P and 1 minus F has also covariance 0, makes the case 0, 0, and still one case is remaining. P1 minus F, and then we obtain the lasting term, which is 1, 0. Okay, so the reason why this implication, this reverse implication works, is that those random variables are, in a sense, too simple. But there are more complicated examples which are quite attractive, I think. There is one that you maybe already know. That's the case when the vector F is a Gaussian vector. Then this implies that this reverse implication works. Because, in fact, in the case of Gaussian random vectors, the distribution is just given by the covariance matrix and by the mean vector. Another case which is quite attractive is the case of vectors which are associated. That means an associated random vector, so a vector which is associated means just that the covariance of some function of f of x, g of x, is non-negative in case f and g are measurable and coordinate-wise monotonic. So and such that the covariance exists again. Okay, so in this case, this is this also implies this reverse inequality. Maybe I should explain why. There is a nice result which shows that in this case, if f and g, so let's say lemma, if f and g, so here x is say with value in Rd, if f and g are functions such that f of x minus f of y is less than the sum from e equals 1 to d of ai times xi minus yi, and analog thing for g, of bg x, I'm sorry for the index, it's xi minus ye. Okay, so this implies that the covariance of f of x and g of x is bounded above by the sum from e equals 1 to I, from e and g equals 1 to d of ae bg with the covariance of xi xg. So this inequality is quite interesting because there is here a relation between the covariance of quite general functions, which are Lipschitz, and the simple covariance. So in a sense, this proves when you specify functions f and g which depends only on the first coordinates, or which depend on the last coordinates, then it will give something like the fact that the covariance of let's say f1 of the past, g1 of the future, is less than the sum from e equals 1 to p, sum from g equals p plus 1 to d of AE BG covariance of XE XG. So E's are small, and here you see what I mean. That means that P is x1 until xp, and F is xp plus 1 until xt. Okay? So this is exactly what we expect. That means when you have a function of the past and a function of the future, it is zero when the covariance between elements of the past and elements of the future is zero. But there is something else which is much more interesting to my opinion, is that if all those covariances are small, then this expression is really small. And so I mean there is something which is a kind of almost independence. Okay? Near independence. So I don't know how much, maybe I shouldn't give all the details, but I will not give all the details. I just write an intermediate result which may be proved very easily, which is the following. If you define f is less than f1, in case f1 plus minus f is coordinate-wise monotonic, then the theorem is the following. The covariance of f of x and g of x, as described before, is less than the covariance of f1 of x and g1 of x. And in this case, the functions f1 and f2 are f1 is the sum of ai xi, and g1 is the sum of b1 bi xi. Okay, so I think you have everything to do the job. So if I give those two aspects of the things, it is just to say that there is nothing to do between mixing properties and orthogonality, which are just geometric properties of covariances, but in a sense those results which are related to association or to Gaussian, because in the case of Gaussian you have almost the same inequalities. So there are things which should be, which if you want to do a reasonable theory, a frame which is large enough, you should assume that such examples are included and such examples also. So in order to understand how it should be done, in the case of such examples, I will take one model. Which is the simplest generalization of this model. Let's say sum of ak ct minus k, for k equals minus infinity to plus infinity, what I will call linear type models. So this model is the stationary solution of the previous equation is this type, and how to do to approximate, to give something related to covariance of the function of x0 and the function of, let's say, xr. I could have done this with vectors of dimension more than 1. That means here the past is just x0 and the future is just XR, but it is just for simplicity. So you can cut this series as the sum for for k less than p of ak ct minus k. That means I just truncate the series, and in this case xt minus xtp is not something important if you have the corresponding moments that just less than the expectation. I didn't say, sorry, something because it was in the same frame, that ct will always be an IID sequence, okay, with moments. And so here you have this times the sum for k more or equal to p of those ak. So that's the tail, the double tail of the series, and also x0p and xrp are independent in case 2p is less or equal to r. So with these relations, we just may control such an expression. So this expression may be bounded above by may be written like covariance of f of xt minus f of xtp and g of, no, sorry, it was f of x0, g of xr plus the covariance of f of x0p and xj of xrp plus covariance between f of x0p and g of x r minus g of xrp. Okay, so with respect to this second relation, this may be assumed to vanish, and we just may bound those things if we assume that f is, let's say, lip f has a coefficient of Lipschitz which is lip f, then this may be bounded by 2 times lip f times the supremum of g times this expression, which was x0 minus x0r, x0p, sorry, in L1 norm. So that's the first term, and the second term writes analogously. So that will be f infinity times the lip g coefficient, and that's still the same expression, which is here. So this means that when p is big, when r is big, then you can choose a p which is big, and so this expression is maybe arbitrarily small, and so this means that you have a way to define, that's maybe a very stupid way, but it works in some case, to define some approximate independence. So I will define it more formally and then pass to examples. So the definition is, I just keep on with the same notations. So we just need to bound above expressions such that the covariance between the function of the past and the function of the future. And so this should be bounded above by some function of f and g times some sequence which depends on r, which is the gap between past and future. I just give two examples of such functions. So I first detailed the example of associated and Gaussian random variables. So for associated or Gaussian processes, okay, I didn't describe what is, I didn't define formally what is an associated process. It is just a process whose finite repartitions are associated random vectors. Okay, so xt is for t in z is associated. That means just that xt for t less than some arbitrary p is an associated vector. Okay, that's a bit more easy to define in the case of in the discrete time than in continuous time. But so in this case, just if you remember the inequalities we had, just psi of f and g should be the product between lip of f and lip of g, where lip of f is the supremum of f of x minus f of y divided by the sum of xi minus yi. So that just I need to define it this way if I want to get this story. And then epsilon of r should be the yes, in this case it should be exactly the supremum of the covariance of xi xg for e minus g more than r. Okay, so with this definition you get that associated random processes are weakly dependent this way, and they are also that's also the case for Gaussian ones. Now, for the examples of those linear processes, you need something a bit different, which corresponds to the function I almost wrote. So let's say I will write this one and maybe C0 of f and g, which is just f infinity times lip f, lip g, sorry, plus g infinity times lip f. So this will fit the story when you put, for this example, you just put something like epsilon r is twice the expression sum of for k more than r over 2 of those a k. So you have still this expression, but it doesn't look such many examples. But at least what you can think is that if you now put psi is psi1 plus psi2, plus psi0. Then you have a notion which will integrate both kinds of examples, and also you can add such example, combine them. Okay. The last notion I wanted to express corresponds to the fact of causal linear processes, which means that xt is just the sum for k more than 0 of ak ct minus k. Then something a bit more easy may be written, that just psi 0 prime is psi f infinity times lip g. And also there is some expression of epsilon, which is epsilon of r is the sum, twice the sum for k more than r of ak in absolute value. Okay, so this expression, this definition fits for very, very simple examples, but we need some more. Maybe I will not detail too many examples. I will just go for one class of examples because I don't have so much time. How much time do I have?
About 20 minutes.
Sorry?
About 20 minutes.
Okay, so I just take 2 minutes to explicit two examples, and then I go to some more technical tools. The first example is, okay, no, I will just take one example, which is xt is a function of xt minus 1 and xt. All over the talk, xt is an IID sequence. So this is a very general way to write Markov chains. And so in the case when expectation of f of 0 and xc0 is finite, and expectation of f of x and xc0 minus f of y and xc0 is less than a constant k times x minus y, where k is less than 1. It means you already can think that here there is some application of the standard fixed point theorem. I don't know how it is called in Russia. In France we call it Picard, but I am not sure in fact. Fixed point theorem. Yes, I think it's better. Okay, so that's to get the existence and uniqueness of such systems. If you don't have such things, by the way, I should repeat about Veretennikov, and you can use very nice works by the very recent Fields Medal Martin Heirer, but I will not have such pretension. So I just explain how to get this. So you take, so here I just take moments of order 1, and I will take L1 of nu, where nu is the law of the vector xc0, xc1, and so on. So that's a law on R at the power n, the sequences here. That means h is the function in L1 of nu, means exactly that expectation of h of xc0 and so on, is finite. So the right space to prove the existence of such a model, of the solution of such a function, is just to fix and to a function h associate a function k, such that k of, so it is defined on sequences, k of u0, u1, and so on, is H. So it should be F, sorry. It should be F of H of U1, U2, and so on, and U0. So this function may be seen to exist, and it is very easy to prove that this function is a contraction in L1 of nu. Okay, so that's a way to prove that simple conditions of contractions are enough to define models. In fact, I just got a very simplified model. You can also put a model which is much more complicated, which are models with an infinite memory, this way. But that's, the proof is essentially the same. Okay. So there are lots of models this way, for sure, Markov chains, but for the Markov chains, there are lots of Markov chains which don't have the standard irreducibility properties, so it's very difficult to prove existence and uniqueness of a stationary solution. I should maybe, no, I will not detail this because I will just lose my time. I want to say about moment inequalities. That means here I will take a sequence x1, x2, and so on, which is centered at expectation, and I am interested into bounding E of x1 plus xn at the power p. So if you don't, for p an integer, so if you don't have any more knowledge, then this is just the sum for k1 is 1 to n, and so on, k2 and so on, until kp is 1 to n. There are p symbols of sums times the expectation of xk1, xkp. Okay? But when you have this, you cannot really understand what happens. So I just want to bound above those expressions. And here you have just sums over k1, kp between 1 and n. So that's an inequality here. And if you want to see a bit more what happens, we shall order those things, those indices, and if you order those indices, then the combinatorial coefficient p factorial appears, and you get this. So it is less than p factorial times the sum for k1 less than k2 less than kp less than n, and then you will understand very soon why I say about the stories. So I have those integers k1, k2, k3 until, let's say, kp. And if I want to let's say this is p factorial times a p of n. Then what happens is that in those terms, in a fixed term like that, if there is independence, for instance, if one of the indices is isolated, then this moment vanishes. So what happens if you don't have exact independence? What you want to say is that here there is a number L such that between KL and KL plus 1, this interval is the largest interval. So you want to write, in this case, that expectation of xk1, xkp is e of xk1, xkp, xkl, sorry, e of xkl plus 1 until xkp plus some covariance, plus exactly the covariance between xk1, xkl and xkl plus 1, xkp. So it looks completely stupid to write this, but if you think about it, you see that here I make appear independence, which doesn't hold formally. So the loss is exactly the expression of this covariance. So a way to bound the stories is just to define some things that I will call C, let's say Cp of R, which is a supremum for sequences k1 less than kp, such that kl plus 1 minus kl is R of covariances of this type, k1, kl and kl plus 1 until xp. So define this. So all the terms will be bounded above the same way once you know the gap between those things. But you see that this set of integers, this set of k, such that k1 is less or equal kp less or equal than to n, may be written as a union of el, sorry, where L is not an index chosen randomly, that's just the place. This means just that those indices satisfy kl plus 1 minus kl is the maximum value of ku plus 1 minus ku. Okay? And so it is also the union for L and R of ALR when exactly this kl plus 1 minus kl is exactly equal to R. So once you have those things, just some comments concerning the cardinality of this expression. So the cardinality of EKR, what is that? ELR, sorry. Those are integers, and the gap between K1 and K2 is less than R, so that means there are at least R plus 1 choices for P minus 2 indices and 0 choices for the others, and there is also one choice. You have also to choose the first one, which is essentially anywhere in the interval of size n. So that means here the cardinality of this set is like this. How to conclude? That's not so complicated. In fact, by using those facts, in fact, you have the sum over all the indices, and so this sum, which is the name was AP of n, is just less then a sum over L over the sum for k in the set EL of the expressions EX K1 EX KP. Okay, and this may be written as, may be bounded above by AL of n, A P minus L of n, plus the sum over P over, over L over the sum over R equals 0 until R n minus 1 of the expressions which are, so the cardinal of E L R times times the expression that I called CP of R. And this may be bounded above very simply from all those considerations. That's simply, so the sum over L may be something like P, because the place of the biggest holes may be between, that's P minus 1 in fact. And then you have n times the sum for R equals 0 to n minus 1 of R plus 1 at the power P minus 2 Cp of R. So this recursion, this gives a recursion for those who are used to combinatorics. There are numbers which are closely related to that, which are Catalan number, which appear very naturally. Catalan numbers are the numbers of way to put parentheses to an expression x1, to a product x1 xp. And that's essentially what we did when we cut such products like that. So Catalan numbers satisfy exactly an inequality which is the one when you suppress these additive things. So that means we can say a bit more and you get some moment inequalities. This of order, let's say, of even orders, because for odd orders it doesn't give much information. So what I will just say is how to get some what kind of inequalities can we get this way? There are two kinds of inequalities, which are the first, the simplest form is the inequalities of the type Marcinkiewicz-Zygmund. So in case Cp of R is less than R at the power, I think it should be d over 2 minus 1 times some constant, then expectation of x1 plus xn should be less than a constant times n at the power p over 2, the integral part of p over 2, with some constant. So this is Marcinkiewicz-Zygmund type inequality, which are useful, for instance, as I will show for central limit theorem. If now, if you just limit yourself to the index p is 4, then an inequality which is known as Rosenthal inequality for independent random variables is something like this is less than a constant times the sum of expectations of xi at the square plus the sum of expectation of xi at the power 4. That means that that's a bit more precise here. This means that you have, in the case when you have IID random variables, this is n at the square, but multiplied by the moment of order 2. And there is one term. So these kind of inequalities are very well adapted to prove triangular limit theorems. Okay. I think I shouldn't go further for this story, and because I wanted to explain a bit about Lindeberg method. Because there is one very central result, I think, in the probability theory, which is the central limit theorem. And I will just explain Lindeberg method, independent method, and then how to extend it to Lindeberg dependent method. So again, you have a sample x1, xn, which are, no, I don't write it with big letters, maybe with small letters it is more convenient. x1, xm, let's say, are random variables with expectation of xi is 0, and the sum of expectation of xi's at the square is 1. From I equals 1 to m. Then Lindeberg method is simply a way to compare the law of the sum of x1 plus x. So that means here you have x1, xm are independent random variables. Then you want to approximate this by the sum of Gaussian and independent random variables this way. You construct independent Gaussians y1, ym, such that yi's is a Gaussian random variable with the same variance as xi's. Okay? So what happens if I will take directly a fast way, so I will take the function f of x is etx, the one associated to characteristic functions, then expectation of f of s minus f of t, this is less than up to some constant, but I think there is no constant, I'm not sure, I don't mind. That means that is less than t at the power 2 plus delta times the sum of the expectation of xi at the power 2 plus delta for e equals 1 to m. If for any delta more or equal to 0. So this doesn't say much when you think about random variables, which are very simple, but if you take xi's, which is big xi divided square root n, then what you will make appear for an IID sample here, you will get something like 1 over n at the power delta over 2 times expectation of x0 at the power 2 plus delta, which means that under a condition of moment of order more than 2, you get some convergence, which is also with some rate. Unfortunately, this doesn't work directly for dependent data, but there is a very simple and elementary way that we discovered to do that. if in this setting I just omit the assumption of independence, then in this case you can construct exactly, so the y's are always independent. In this case, what happens is that you have x1, xn, xm, and there exists x1 star, xm star, which are such that xi star has the same law as xi, and x1 star, xm star is an independent vector. In this case, what happens with evident notations is that E of f of x of s minus f of s star, where s star is simply the sum of those xi stars, is simply by independence of those things, it is the sum of expectations of f of x1 plus xi minus 1 plus xi plus xi star plus 1 plus xm, and I put it under it to understand how I do this sum. So x1 plus xi minus 1 plus xi star, and then xi plus 1 star, and so on. So what is this term? So I may come from E equals 1 to m, something like that, with some conventions. And so this is written like a sum of delta i's. No, delta is not a good idea. Delta big. And in delta, what happens is that all these vectors are independent. So in this case, delta I from independence is just E of f of x e plus 1 xe xm star. This because of the form of the multiplicative property of the exponential. So there is independence of this, so you can do it like e of f of x1 plus xi minus 1 plus xi minus f of x1 plus xi minus 1 plus xi star. But this is, so I want to bound this above. This is the expectation of a number which has a modulus 1, so this is bounded above by 1, and this is less than the covariance of f of x1, of x1 plus xi minus 1 and f of xi. So how to use that in the frame? How to use that in the frame of the central limit theorem? In fact, if now you have a sequence of random variables, there is a very old method, which is the method of Bernstein blocks. Which is quite elementary, but you have a sample with size n, then what you want is to put the samples with blocks of size p and q and p and q and so on. So that means here you will construct x1 is x1 plus xp divided square root n and so on. So here you have the first block, the second block, and there are exactly m blocks, let's say, where bm exactly is this bg is a set, let's say p plus q, that means p plus q g minus 1 plus 1 until p plus q g minus 1 plus p. So this is this set of integers with cardinality p, and in this case the sum of xi divided square root n writes as x1 plus xm, which will be bounded by using the idea of Lindeberg method, plus some remainder term, which is the sum between which can be shown to be negligible. So what is necessary in this story? It is really necessary to know about bounds for e at the power something more than 2. And to do that, you need, for instance, inequalities of moments of order more than 2 that I developed just before. So that's just a way, but a very, very naive way to get central limit theorems. There are much more intelligent ways, but in a very general context, that's not so easy to do that. Okay, so maybe I should. I don't know if I was comprehensible or not. I have a few time.
So probably we have time for one quick question. Maybe you can give some references on your books or whatever, where people can.
Yes, sure. In fact, there is so these stories. There was a paper by Sanal Ricci and me, from 1999 in stochastic processes and applications. And also there is a book with many applications from 2007 with a number of co-authors, which are De Decker, Lang, Léon, Prieur, Luigi, sorry, and Prieur, and we did a lecture notes in statistics number 190, which was published in 2007. But in fact, there are lots of other applications. I just stressed the most elementary facts, which are already essentially in this paper of 99. But there are lots of applications to many fields in fact, where those ideas of weak dependence may be used in, really. That's this is not the solution to everything, but at least it can fill some simple results.
That's English speaker again.